Chapter. I didn't realize the time. Is it Cafe con Chemistry already? Well, let's continue from where we left off and discuss a little bit more about the theories of chemical kinetics. In today's discussion, we will focus on collision theory, describing collision frequency, molecular structure, and collision energy. We will also cover the Arrhenius equation and transition state theory. We have already briefly touched upon collision theory, which is based on the assumption that particles must collide with one another in order to react. However, there are a number of factors to take into account, including collision frequency, molecular structure, and collision energy. We will go over the importance of each in the role in collision theory. Let's begin with the principle foundation particles must collide in order to react, which relates to collision frequency, or the number of collisions per unit time. Concentration plays a key role in collision frequency because the more molecules present, the more potential collisions that can occur. However, another important factor is temperature. As we mentioned before, temperature affects the rate constant and the rate of reaction. And it has been shown that the rate constant increases as temperature increases. This occurs because as temperature increases, so do the frequency in which molecules collide. Also, if we are increasing the collision frequency, we are increasing the probability in which collision event will lead to a reaction. An empirical model that is used to describe this phenomenon is known as the Arrhenius equation, and is as follows. Let's review this equation by discussing the relationship between the rate constant and temperature. As temperature increases, the value of that negative exponent becomes smaller, results in an increase in the magnitude of the rate constant. We see at higher temperatures, the rate constant is larger, which results in an increase in the rate. The term E sub A is known as the activation energy, which is that threshold energy, or the minimum amount of energy that needs to be met for the particles to react. If particles collide with less than the minimum energy, they bounce off of each other and do not react. However, if they can overcome this threshold energy, when they collide, then they form an arrangement of atoms known as the activated complex, or also known as a transition state. This can be displayed graphically as follows. These reaction energy diagrams can graphically describe how the potential energy changes as the reaction progresses from reactants to products, including relative energy levels of reactants, products, and transition states. These diagrams also tell us whether reaction is favorable by calculating the enthalpy of the reaction, which is equal to the activation energy in the forward direction minus the activation energy of the reverse reaction. If the enthalpy of the reaction is exothermic, which occurs when enthalpy is less than 0, then the reaction is favorable. This is displayed in a figure A, where reactants A and B form an activated state and forms the products C and D, and is energetically favorable. However, if enthalpy is greater than 0, then the reaction is endothermic and is not energetically favorable, as shown in figure B, because the products have higher potential energy than the reactants. Going back to the Arrhenius equation, it is important to understand that even though you increase temperature, your activation energy never changes. Only the number of collisions with enough energy to overcome the threshold barrier increases. Looking back at the equation, R is the universal gas constant. The Arrhenius equation allows us to solve for the activation energy, and one such way we can do so is by rearranging the equation in the following way. By doing so, this allows us to graph it and follows the equation for a line, and our slope is synonymous with the activation energy. Or we can look at two different temperatures and set these different equations equal to each other and subtract them, which condenses to the following equation. Now, you must be wondering what A stands for. A is known as the frequency factor, which takes into account collision frequency and the probability of structural orientation. Structural orientation is important because not only do you have particles collide and meet the minimum energy to react, but you also need your reactants to collide in the proper orientation, and this is known as an effective collision. This figure gives a good visual for an effective collision because in the first two instances when nitrogen monoxide collides with ozone, there is no reaction because they are not in the correct orientation. However, the third instance, it does react because it is in the proper position. If we were to take the same reaction and draw a reaction energy diagram, it would look like the following. The transition state, or the activated complex, which is an unstable species that cannot be isolated. Even if you reach this high energy species, it does not mean that your products will form because it can go in either direction. Hopefully you enjoyed today's discussion, which was packed full of interesting topics. We covered collision theory describing collision frequency, molecular structure, and collision energy. We also covered the Arrhenius equation and transition state theory. Thank you!